Hi, welcome to your tutorial on Dalton's Law of Combined Pressures. Remember John Dalton? He's the guy who gave us something that's pretty close to the modern atomic theory that we use in the early part of the 19th century. John Dalton, English school teacher and chemist. So, it was John Dalton who figured out that if you have a vessel with multiple gases in it, and that mixture of gases is being held at some amount of pressure, that none of those gases are completely making up that pressure, but rather each of them is making up a small part of it. So the total pressure of the system, of all the gases, the total pressure of the system is equal to the sum of the pressures of each of the individual gases. Well, this seems pretty easy, and in fact, it is. If we have a total pressure of, let's say, 760 torr, normal atmospheric, and the pressure of gas X is 312 torr, the pressure of gas blue square is equal to 115 torr, it becomes pretty easy to figure out the pressure of gas purple triangle. Let's set it up. Okay, the total pressure minus the pressure of the two gases that you know is equal to the pressure of the remaining gas. So when we plug in numbers, what do we get? There we go, 333 torr is equal to the pressure of gas purple triangle. And I'm using these symbols just to indicate that you can do this with any gas. You can also do it with 2 gases, you can do it with 100 gases. I just use an example here of a mixture of 3 gases. Okay, now, why would we use something like this? Well, we use it because of a common method that's used for collecting gases when we're running a reaction and one of the products is gaseous. To collect a gas over water, we'll need a couple different things. We've got some sort of measuring device, such as this graduated cylinder. We have this, which is called a pneumatic trough. And it's just a metal tray, or sometimes plastic, with a small spout here that you can attach this tubing to. Now, we'll fill the pneumatic trough with water. Of course, we can't do that until we've done one other thing. We have to attach the tubing and clamp it off somehow. And then we can fill the pneumatic trough with water. Now, the next thing we're going to do is take this graduated cylinder, or some other sort of gas collection device, and we're going to invert it over the small opening in the bottom of the pan. That'll look like this. So now that our graduated cylinder is upside down, oops, I forgot to do something. First we have to fill our graduated cylinder with water, all the way to the very top. So, I'll do that to indicate that that's full of water. Now we invert it. Okay, so now we've got this column of water with some nice little markings here on the side that indicate volume. And we've got this spout, we've got this trough, it's full of water. Where are we going with this? Well, this is a method that we use to figure out the volume of a gas that's produced as part of a reaction. So now we just need a reaction. Okay, here's an old standby. Okay, well, now we have a flask. That flask has a small piece of glass piping coming out of it. It's tightly stoppered, and attached to that glass tubing is our tube that's going to go into our pneumatic trough. Now we just need a reaction. Well, if we take a little pile of baking soda, and to that we add some vinegar, what happens? Well, we get a reaction because we've added sodium hydrogen carbonate, or sodium bicarbonate, baking soda, with acetic acid, the active ingredient in vinegar. We get a neutralization reaction, and we produce water, sodium acetate, yes, and this stuff, CO2. Now, we can find the mass of the CO2 by just massing the reactants and the products that we have left in an open vessel and seeing what the difference in mass is. That would give us the mass of the CO2. But if we need to know the volume of CO2 produced, we're going to have to capture it in some apparatus like this. Now, when we capture it, when those gas bubbles begin to form, where are they going to go? Well, they're going to go right straight up this tube, and they're going to go into this graduated cylinder. And they're going to displace some of the water in the graduated cylinder. So the amount of water in here is actually going to drop. We're now going to have a new water level, and up above that water level we'll have a bunch of CO2 gas. Now, that's fantastic. We now have captured our CO2 gas, and we could measure its volume, and we could figure out its pressure and its temperature and all those other things. There's just one problem. Water is kind of clingy. So as the CO2 gas passed through the liquid water, as it breaks the surface and starts to form a layer of gas over the water, some water molecules will be pulled along with the CO2. Water does this all the time anyway. It's constant. A few little particles of water at any given moment, at any temperature, are making the escape out into the vapor phase. It's called evaporation. It's happening all around you right now. But in this case, what that means is that what we think is just CO2 gas is actually a combination of water vapor, water gas, and CO2 gas. Oh, well, if we find the volume and the pressure of the CO2 gas, we're also including some amount of water vapor. This is called the partial water vapor pressure. And it depends on the temperature. The hotter it is, the more water molecules at any given moment are escaping, whee, I'm free, from the surface of the liquid and turning into water vapor above the liquid. We can look this up. Didn't you know? There'd be a chart. So let's say we've run this whole reaction, we've collected our gas over water, and now we want to figure, we don't know the pressure yet, but we want to know how much of the total pressure of the gas that was collected over water is likely to be made up of water vapor instead of our CO2 gas. Well, we can go to this sort of chart. This is a water vapor pressure chart. If you're using Holt Modern Chemistry, it's on page 898 in Appendix A. It's Table 8A. And what it does is give us a temperature for the water that we're working with, and says that at that temperature, this many millimeters of mercury, or torr, or this many kilopascals, that much of the pressure is going to be comprised of water vapor. Now, we measure that based on the temperature of the water itself, because of course the water is what's making the leap from liquid to vapor. So, if our water bath was at 20 degrees Celsius, and that's pretty common, what we would be looking for would be this column. Well, if we are measuring in torr or millimeters of mercury, that means that the partial water vapor pressure in this case would be 17.5 torr. And thinking back to the law of combined pressures, we know that the total pressure is equal to the pressure of the CO2 plus the pressure of the water vapor. And we said it was what? 17.5 torr. We're going to list our variables. Okay, so the vapor pressure of our water is 17.5, but we're still missing two things. What we would like to find is the pressure of our CO2, but we don't know the total pressure yet. How do we get that? Well, for that, we need a barometer. Here's a barometer. We'll use a barometer, not this one, to take a reading of the actual barometric pressure or atmospheric pressure in the room at the time that the reaction was run. So, for our purposes, let's say that atmospheric pressure today in this room where we've just run this reaction is 772 torr. So, what does that tell us the pressure of the CO2 is? Well, we just solve for CO2. Okay, there you have it. So the pressure of the CO2 alone is 754.5 torr. Of course, that's too many sig figs, so we would have to say that 755 torr was the pressure of the CO2. This is sometimes referred to as the pressure of the dry gas because, of course, what have we subtracted out but the vapor pressure of the water? Therefore, now we're looking at the gas alone, or the dry gas, without the pressure of the water included. Okay, you'll have some practice with these, and then we can talk more about adjusting volumes. Have a good day.